Good morning. My name is Reza, and I'm a learning alcoholic. I started underage, and my parents didn't mind. My father had just passed the bar exam, and like a good bartender, he hooked me to a stream of book series. It was addictive. I had a lot of thirst, and I overdosed many times. I slept less and worked faster to save time for my passion. I had 2 eyes, but they weren't multi-threaded. I even learned to read quickly. I employed a skipgram, striding, pulling, none worked. I went to Sharif, Berkeley, and MIT to learn from the best. I was living in Boston. It has Irish roots, and as you can see it here, it's a great city to live. But the prospect wasn't looking good. There was a deterministic game plan, and I had to follow it. It was this. The plan was this. You have to specialize, publish to reach to a lot of people, and then mentor students to move the torch of science forward. I was a scientist. I did a little bit of back propagation to my postdoc layer, and I didn't like it. The gradient was screaming for me to make a dropout and break the cycle. It was truly sad. It was really, really sad and depressing. It's sad when you realize that there are many, many interesting things that you like to read and learn and do search about them, but you cannot. Just to give you a hint, every day we are publishing about 20,000 scientific articles in the world, and most of us, most humans, in their entire lifetime, they will not be even able to read 100 articles. So the story I made up is a sad revelation that has happened to a lot of scholars in the past generation. I made a bit of exaggeration to make it fun, but it's true. It was even sadder when we didn't have printing machines or when we didn't have the, let's say, the writing, or perhaps even earlier when we couldn't speak. We were not human, maybe. However, with AI, it gets happy. There is a happy ending. Now with AI, you can read lots of articles. As a matter of fact, I can go to have a coffee break, and by the time I'm back, my algorithm has read all the wiki and all the scientific articles we have in our depository. I wouldn't even have time for my coffee to get cold. I usually try to use a smaller cluster size, so I would have some time to think. But that's the future. We are glad that we are able to use Spark and Claude because they solve one problem. We can read all the science. That's not a problem anymore. But we are trying to make sense of it, and that's what the talk is about. So I'm coming from Elsevier. You may know Elsevier from this tree. It's a publisher. It's a B2B. It usually provides a subscription to companies. So you may not recognize it, but you may see this sign on the articles, or you may have used the Science Direct in your academic career to access articles. Or furthermore, you may have used the Scopus, our citation and article search platform, to follow science trends. Here is how we introduce our company. We call it an information analytic business. We used to be a publisher, but now it's a lot more. Publisher provides us with content, very valuable content. It's peer-reviewed. We have copyright. It's millions of articles. But that's not our strength. That's only one part of it. And the next part is about technology, how we drive insight from this. OK. Here you can see a transition of publishers and companies like us, and perhaps you. We used to be a provider of material, perhaps in a print versions. And in 1990, we started to have Science Direct. We could go there and do a search. That was great. But nowadays, we are far from that. We are trying to do this, give you recommendations, answer questions, or provide summaries of articles. And this is what has enabled us to be an actionable knowledge, what we call. OK, I wouldn't talk any further about my company, but I'm wondering how many of you actually know Jeff Dean. That's this guy, very friendly. So the Jeff Dean is one of the main innovators of MapReduce, or at least one of the co-authors of the famous MapReduce articles. He started in Google to do that in 2004. In 2011, he started the BRAIN project, what we may now call it the TensorFlow. There is a message here, and the message is that you need a scalable compute to be able to use advanced machine learning, to be able to process lots of data. And nowadays, thanks to Spark, we have that. That's one part of it. And you can see two missing bullets in the middle. In 2006, AWS started to offer the cloud. And Google started 2 years later, and all of you know what happened to AWS cloud versus Google. So being able to have a scalable computations, ideally on the cloud, will enable us to process lots of document information and anything. Okay, that was introductions. I just wanted to give you a story of how our consumption of knowledge is changing. In future, we may have machines like Watsons or a lot more smarter to actually help us understand and read tons of information. Okay, the next part is why I need deduplication and disambiguation. The main reason is our product, Scopus. Scopus is the biggest repository of scientific abstract and citation. However, what makes it unique is that we are actually disambiguating all the entities. You can track citations because we can say that a citation refers to which document. We can track people, we can track organization and their affiliation, and that enables us to provide a lot of analytic inside citation metrics, and that builds essentially lots of products for us. Just to give you an idea of the data model we use in the Scopus, we have articles, roughly about 70 million articles. In articles, we can track authors, and we can track affiliation and their organization and such. So the author disambiguation, the main point of this talk, we have a legacy technology to do the author disambiguation. It's lots of manual rules, a lot of, like roughly 20 million manually curated author profiles. I shouldn't say author profile, but authorships, meaning that an author has written these articles. We are collecting feedback from users in the Scopus, in the Mendeley, in other platforms, in our review, and blah, and blah. And this makes it a smart algorithm. It has roughly a recall and precision of 95%. But that may not be enough, because despite very high precision and recall, it cannot work well. For example, it cannot disambiguate Asian names as well as we want. And the reason is that there is a lot of similarity. Just to give you an idea, if you look at the Zhang name, under this name, we have almost 250,000 of publications. This means that we have publication practically in every university, every journal, every year, every department. Sometimes the same name in the same lab, in the same article. So it's very difficult. The historical approach for disambiguation was based on clustering. But the problem with clustering is that even if you keep a very, very low threshold, what would happen is that all this cluster will be aggregated, and then you need to adjust your algorithm in a non-ending loop. So I'm going to present another alternative today. And that's supervised algorithms, how we can benefit from lots of feedback that we get from users to improve these algorithms. So just to give you an idea about deduplication and disambiguation, they are mostly the same problem. The difference is that in deduplication, you expect a lot of similar fields in two documents. They could be missing, but otherwise they should be very similar. In author disambiguations, we are looking for rare similarities in a few fields. Even the publication year can have gaps. So it's a bit more complex, but from the practical point forward, we can just assume that they are the same from the implementation. So to perform deduplication or disambiguation, what we usually do is that we create something called blocks. The problem is that we have millions of articles, and we cannot compare all of them together. It's an n-squared problem. So we create candidate things, the things that we think they are similar. Like, for example, what we create with sim hash. And then among those similar document, article, object, item users, whatever it's your application, you would say that you would apply a rule, a hard-coded rule, for example, if only 2-bit differs, or even better, a machine learning algorithm, a supervised machine learning algorithm that will collect at a lot of features for candidate document that can be duplicated and would say whether they are the same or not. So it's a pairwise binary classification at the heart. And then you look at all those connections that you make, like a small connection between a node in a graph, and you aggregate that, and then you can build a graph of authors or all the duplicate versions of a document. To give you an idea, I have this holistic plan here. Sorry that you cannot read it. But the main point here is that before you start to build all these pipelines, you want to make sure that you have an evaluation set up. It's just hopeless to build an algorithm and work on it without really being able to measure it. And in this kind of problem, you have two kind of evaluations. One of them is accuracy metric, how good is for your case. For example, your precision and recall. But the other metric that you have to also track is the computational cost. Because you can essentially make your block bigger and bigger and bigger, and your recall will go up, but it comes at a very expensive cost. So we look at that. So we have a lot of components here. You can see from the above, it's a data intake. We get the data, we process them, and then in the processing, we build features on the article level, like normalized names, normalized geolocations, perhaps the content encoder, as I would talk about them further, some statistics. For example, there is a name in an article, and it may be the same as another name. I would like to have something like a document frequency for that name. That's one step. We call it pre-processing. And then we go to a blocking algorithm. It creates sample pairs. And at the heart of this algorithm, I don't know if you see my mouse. OK. Yes, so it's pairwise learning. And it creates a machine learning algorithm that learns on millions or 100 millions or billions examples if two documents are duplicate or two authorships correspond to the same person. After that, you would like to post-process those pairs because every pair comes with a score. You may apply a threshold or look at another machine learning approach to aggregate or perform a ranking. And from that, you get the clusters. And then you may also post-process cluster, merge them, or split them and such. The important thing is to be able to measure all the processes independently so you can perform, as you can see in the accuracy part here, you would be able to perform some accuracy measurement on individual items, which would be ideally a greedy optimization, and also on the holistic end-to-end approach. So I'm not going to talk further about this because it may not be very applicable to all of you, but I would like to talk about other aspects that likely will benefit most. So I briefly talked about the content encoders and how we look at the similarity features. For example, we have citations. You can also think simply of adding a jacquard between citation, between the names. That's one way to go, but it becomes very, very difficult. One reason is that when you look at the jacquard, for example, two articles may refer to very similar articles, but simply because their citation index is different, they would look totally different. So we would like to be able to transfer everything, literally everything, in our organization, all the entities that we have, to a vectorized model of their content or content preferences, and that's what I'm going to talk further. So to just give you an idea, if you think of two users, you can track users if you know they have the same user ID. For example, they are using the same email, and that's not an organization email in different products. That's just pure equality. Then you can also think of a bag of documents, IDs, objects that they are buying, looking, watching, downloading, everything. And that would give you a set comparisons. the item in the set should still have a big overlap. They should be big, so you would be able to compare people or objects. And eventually, and ideally, you would like to have encoded documents or item. So the reason is that if you have encoded document and item, it's not a hot encoder, it's a vector. So if person is writing 2 articles, you can average those 2 vectors, and it will give him an authorship vector. If he's reading 10 articles in the past days, you can also average the vector of those articles, and it will give you a transient perspective about his personalization or reading interest. So if you look at this is some of the entities that we are looking at in our organization. We have reviewer, editors, author, advisors, news, jobs, funding, all of this. The good thing for us is that all of these things can be related to some text, and then we can create a vector for those texts, and all of a sudden we have a central encoding platform. It's a kind of fingerprint for users across different activities that they can do. This central encoding makes the recommendations and personalization very fast and feasible. The alternative technique is that something like this. We have a product, we value it a lot, and we build a very highly customized recommendation between that and another product or another field. And the problem here is that as we have a lot of different products, this is not going to scale. It requires a lot of manpower, a lot of customization, and it would not work. The previous approach I told you, it gives us a very good starting point for recommendation and personalization, and also to be able to track users across all products and give him insight. So I spoke about document encoding, and let's say how we do it. The traditional way is to apply TFIDF, time frequency, inverse document frequency. It's a hot encoder. It's good. It works in many areas, but there are a bunch of problems with it. First of all, it's not suitable for streaming processes. You cannot calculate IDF from a streaming. You have to assume a prior for that, and it's not going to work well. It's a hot encoder, and in that way, it lacks semantic similarity. I mean, if I say Monday or Tuesday, the similarity between that is the same as Monday and Spark. That's going to work well. And it's a sparse representation. You have to usually pick 10K word or something like that. And the problem is that in most of the machine learning libraries, the sparse representation have to be eventually transformed to a dense representation. So it takes a lot of memory. It takes a lot of dimensions from your feature vector, but it's not very good. Another approach that we use sometimes is that if you have access to curated data, for example, classification, science classification, countries classification, estate classification, they are also good. We also use them. But one problem is that you cannot very greatly define a distance between them. For example, think of USA. It has 50 estates, and you create a location tree there. OK, you say Massachusetts and California, the distance between them would be the same in a tree classification as Massachusetts and New York. That's not good. And the other problem with this tree classification is that they cannot represent interdisciplinary work very well. In the science, we have bioengineering. It's a combination of engineering and medicine. So if your class wants to come something between, it doesn't work well. You have to change the tree. The structure is rigid. It changed over time. So 10 years ago, maybe we didn't have bioengineering, and now we have a bioengineering tag in an article, and we may not realize that they are actually talking about the same thing. So instead, we use word-to-vec algorithms, or its many variations, as I spoke, to encode a piece of text. The good thing is that once you have that encoding for a piece of text, let it be a title, an abstract, a paragraph, a sentence, a full text, a journal, an article, you can essentially aggregate it, look at a smaller windows or bigger windows, and find similar things. One of the features I use also for my author-disambiguation is actually the encoding of documents. We aggregate the encoding of document for the cited document, perhaps for the citation, for affiliations and journals and everything. So not only we look at the set similarity, for example, the citation list, citation document ID, but also we look at the content behind the set. So that's one efficient way to do it. So it's just to give you a further idea how this works. I'm showing this hypothetical database that we are using, or we would like to use. You can see a list of our different products here, and what I call it a facet, or its description, is the way that people interact with a product. For example, in Scopus, a user can search a document or write be an author of a document. He may have been a reviewer for that and editors. In Mendeley, he may have read an article, put it in the library. So all of these things can be summarized into a set of documents. So you can see it here. And we can then say that this user has interacted with this kind. We have this kind of interaction from him, like in this table. Sorry. In this table, like he has been an author, a reviewer, and editors. And then for all of this interaction, we can essentially come up with a vector, a vectorial summary. And for that vectorial summary, you can append those vectors together, and then it would be a good starting point for a personalization. OK, that would be, I guess, enough for encoding. Also want to add something about streaming and how to go for a delta algorithm. So what you are seeing here is, let's say, a scalable design stage. And you have to think where you are in respect to your scalability. First of all, you can have a scale-up algorithm, essentially a multi-threaded algorithm running on your laptop or your local cluster. You need a very big machines to process lots of data. We already know that's not good. That's why we use Hadoop or Spark. So then we have a scalable machines. It's good. We have a lot of compute. And ideally, we would like to be able to test things in a, let's say, commercial cloud. The reason is that the on-premise clouds, they don't really, OK, they are scalable. They can be very big, but they are still very rigid. So you may not recognize the dependencies that your program is doing. So that's one level to be able to have a scalable machines compute power. But also we would like to go one level further to have a scalable data, like when you have distributed data. That's also one level. And then the very next level, we can talk about a scalable machine learning algorithms. There are many machine learning algorithms. A lot of them are not scalable. You cannot update them in parallel, or you cannot use partitioned data to do it very well. So currently what I'm doing is using several Spark clusters sometimes at a time to train multiple models in a parallel. That's one way. That's good. We can call it parallel data, parallel models. But even the next approach is to make sure that ideally your algorithms are working with delta or a stream. And to do so, you can only pick up a few machine learning algorithms. The reason is that then you only need to work with the subset of document or subset of the data, and then you can scale better. I mean, the ideal case is that I get one data record, read from the disk, I don't need memory, and I write it to disk after processing. So if we get that kind of machine learning algorithm, that would be fantastic. So another point about employing delta or a streaming algorithm is that sometimes we have an algorithm in place, like in our case, we have author profile that have been used in many products. People are using them. People are then referring to them. So you cannot just come up with a new algorithm for clustering and then come up with a totally new algorithm with a totally new clusters or author profile. So you need a smooth transition. So we need an algorithm that works on the new document while initially it is emulating what the old algorithm was doing, and eventually can get better because it employs feedback. So that's one reason that you want to work with this delta algorithm. The other reason is that not all documents or not all records are equal. Typically, historical records, they are lower quality, and people expect less from them. So if you build an algorithm that works in batch, works for all the documents and all the records you have, it would be a suboptimal algorithm. It would not work very well for the new document that matters more. And eventually, the streaming model, it takes a bit more time to develop and code. But it gives us a lot of computation advantage. And the other difference here is that with streaming, you can essentially do A/B testing. Because the typical clustering algorithm is a batch process, you use this algorithm and you use all the data you have. You cannot do A/B testing. In the streaming, you can try multiple algorithms on multiple documents or multiple streams of the data and then get an A/B testing platform. So this is my last slide before conclusion. So just some advice on how you construct pairs for the simulations. The one point here is that you want to be able to maintain causality between your data. So if you are making a streaming model, make sure that, for example, you have a pair from the document base and a pair from Delta. And the other subtle thing here is that for the train, you want to maximize the randomness of pairs. So pick all the pairs. But for evaluation, you have to actually go for one document and get all the blocking things you get from that so you can do an end-to-end evaluation. So here's the conclusion. I just wanted to say that we can employ the Spark, the Cloud, and all those things to read and hopefully learn from the scientific texts. It's also good to try your deduplication and author-disambiguation or user-disambiguations with a supervised model. The place here is that you first build a model which says if these two items are the same or not. If they are the same, OK, you keep the same existing profile, and otherwise you just design a new profile. We could use the Word2Vec family of encoders to build a fixed size representation of content for all your entities. And eventually, just keep this maybe as the last message, take-home message. If you really want to have an efficient and a scalable ML algorithm, think to build it with a streaming approach. Think to build it with a mini batch or a stochastic gradient learning and such. Thank you.
We have 3 minutes for questions. Any questions?
Thanks very much, Reza, for this nice presentation. My question is, you use supervised learning. So where did you get your labels from?
As I said, we have a legacy system. It's been an unsupervised algorithm, but it has been also backed by a big team of curators that correct it, or from the user feedbacks, or because we also have paying customers that they want us to track their publication records, so we very carefully curate those profiles.
Thanks very much.
But just to give you an idea, you don't really need a training data. You can start from a very, very simple algorithm and apply these supervised things iteratively, and it will get better.
First, thanks for the presentation. My question is about the streaming machine learning. If for streaming you are referring to just the application of the model or the training that has to be trained on some live data that is coming. On this I haven't...
So this is a work under...
Could you repeat the questions, please?
So my question is about when you refer to streaming machine learning, if it's referring to the training that has to be on the stream, if you are using a streaming for the training, or it's when you apply the model, it's just you apply some live data, the model that you have trained on some offline data.
So you can update the model with the live data via streaming. But what I meant is that the model should be able to look at the existing solution, existing things, and get a piece of new data, offline or online, doesn't matter, and then update itself accordingly.
Okay, it's the refining of the model.
Sorry?
It's just the refining of the model on the streaming, okay.
Yeah, updating the model with the updated data.
And do you get some feedback about how do you evaluate that the evaluation of the model is wrong on the streaming?
Well, we are matching our algorithm with existing solutions. We have also gold data set. In the one good advantage here is that you can change your time reference, go a bit back and forth, and then you get a new data set. You can train with it for a while, and if you think you are overfitting that, and then you move the time window a bit forward, and it's just like fresh data on scene. So we check with the existing algorithms, and when we make our predictions, it takes maybe 6 months for users to look at their profile and give us feedback. So over time, we can also see if users ask for a correction in their profile.
All right, that's all we have for now. Let's give a huge round of applause to Reza Karimi for an excellent talk.
Thank you.